Today under statistical thermodynamics, we will be looking at few of the thermodynamic functions in terms of partition function, and the first function is entropy. So entropy, this could be written as S is equal to KLN W also, and this value of W could be obtained, and the entropy will be S is equal to NKLN Q by N plus NKLN dln q by dt plus nk, and we could take nk common and we will have this. Now this n into k, so if n are 1 mole, then this n into k we could write it as r, that is real gas constant, and q by n could also be written as capital Q, which is the molar partition function. And in many books the value of 1 is neglected as it is very small as compared to all those values. So in some books you won't see this one also. I have taken it from Puri Sharma Pathania, and over there you have one is used. The next thermodynamic function that we'll be discussing is work function. Now work function, it is represented by A and it is E minus Ts. So we have the value of internal energy and we have the value of entropy. Now in few books E, it is written internal energy is represented in the form of U also, it could be represented in the form of E also. So we know the expression for internal energy in terms of partition function, we know the expression for the entropy in terms of partition function, so both could be substituted. Now this RT, when we multiply with this, we have RT square, so this and this, both these terms will be cancelled out. We could neglect one as I said earlier, and hence we will have minus RT ln q by n, and again this q by n could be represented in the form of capital Q, which is the molar partition function. Small q is the partition, individual partition function for individual system, and capital Q will be the molar partition function. The next thermodynamic function that we'll be looking it is pressure. Now pressure, that is rate of change of work function with respect to volume at constant temperature, will give us pressure, and we will be using this expression for work function in order to obtain the pressure, and we could expand this, that is work function A is equal to minus RT ln Q minus RT ln N, and then we will be differentiating it with respect to volume at constant temperature. So N is constant, so this will become 0, and we are left with minus RT dln Q by dV at constant temperature, and this we know it is equal to negative of pressure, so both sides negative will become positive, and hence we are left with P is equal to RT dln Q by dV at constant temperature. So this is the expression for pressure in terms of partition function. Next we have heat content in terms of partition function, and heat content it is also known as enthalpy in terms of partition function, and enthalpy is given as H is equal to E plus PV, and or in pure books it is written in the form of U also. So U plus PV, and we could substitute the value of internal energy in terms of partition function as well as pressure in terms of partition function. So from both the terms RT could be taken common out, and this T could go in the denominator over here, so differentiation, that is dt upon t, could be written as dln t. We have dt upon t, so this could be written as dln of t. Similarly dv upon v could be written as dln of v. So we have written both the terms, and this is our final expression for heat content or enthalpy in terms of partition function. Thank you very much.